Okay, so here's the last kind of big, all-encompassing topic that we have, and that's thermodynamics and gas laws and buoyancy, and it all kind of plays out the same way. Because
I was just doing the thing between the words you were saying.
okay, you get it in.
Yeah.
Too.
What?
Okay.
I did, yes. There's also a line where my hair changes color right here.
Joel, you have eyes.
Okay.
I do. It changes color like on the side of my head. Because this is all hair that's been exposed to sunlight, and this is hair that has never been exposed to sunlight, so it's a lot darker.
Okay. All right.
Hi.
There's your hair color lesson for today.
Yep.
Okay.
Let me get it over there.
So the cool thing about thermodynamics is that if you look at what allows us to have a modern civilization, it's our understanding of the laws of thermodynamics. Okay, because it allows us to cook food. Okay, it allows us to, whether that be on a cooktop, whether that's a microwave, whatever. It allows us to heat water up and turn it into steam and heat the steam. And, huh?
I said Q equals MC delta T.
Wait, what?
Q equals MC delta T.
That too, which we'll get into that equation tomorrow.
Chemistry.
Okay, and because you know, if you think about how civilization would be different, let's say that for whatever reason we did not have the capacity to burn things. Okay, whether if you go back even into, you know, the cavemen, if we did not have like a carbon-based plant or wood or whatever that could burn, or we could cook meat and produce fire and produce warmth, we would have never gotten to this point because of the fact that without that capacity to cook food, without the capacity to boil water, there's a whole bunch of things that we would not be able to do. So by virtue of the fact that whether that's cutting down a tree, whether that's burning coal, whether that's burning natural gas, whether that's burning gasoline, a tremendous amount of our existence comes from what's known as an exothermic reaction. Exothermic reactions give off energy. So you go in today and you start your car, boom, you turn on the engine, gasoline explodes with the oxygen, it releases heat, okay? And a bunch of excess gases, and that's what drives your car. So it's kind of a cool deal. So one of the things that if you study AP chemistry, you see that nature likes two things. Nature likes disorder, and it likes situations where heat is being given off. Okay, those are the two favorable situations for nature to exist. And so this is why we've been able to cook meat a lot longer than we've been able to freeze it. Because freezing meat is tough, because, or making ice or whatever, because you'd have to have endothermic reactions, which take energy in, versus exothermic reactions, which give off energy. So imagine that if you light a fire, and instead of heat being given off, it actually takes heat from the environment and takes it into the fire, okay? If it was an endothermic reaction, it's like, oh, wow, it's really hot in the room, let's start a fire. That's how we can cool it down. And that would be the equivalent thing, as opposed to, wow, it's really cool in the room, let's start a fire to warm it up, okay? But that's the fundamental shift. And so one of the things you have to, especially from a physics perspective, is keep straight, is the difference between temperature, okay, which is a measure of the individual particles, versus heat. So when you're talking about temperature, and in a physics classroom, typically we measure temperature in units of Kelvin. So if you've never experienced the Kelvin scale, all you have to do is take the temperature in Celsius, it's an easy conversion, and you add
273.
273 to it. So like right now, the temperature in this room is probably about 20 degrees Celsius. So if you add 273 to it, you get 293 Kelvin. Okay? Now, here's the advantage of the Kelvin scale. You have two primary advantages of the Kelvin scale. One is that in the Kelvin scale, your temperature never goes below zero, so it never goes negative, okay? And theoretically, it can't really even reach zero, because once you reach 0 Kelvin, that's what's known as absolute zero, okay? And at absolute zero, entropy, which is a measure of like the disorder in the system, drops to 0. So that's 0 degrees Kelvin is a theoretical limit on how cold something could get. So like even like the universe itself, we're at about 0.3 Kelvin, okay? So that's like the temperature of the materials in the universe. So the advantage of the Kelvin scale is that, unlike, like for example, the Celsius, okay? And you'll see why this works in terms of the gas law in just a second, okay? At 0 degrees Celsius, what happens?
Nothing.
Water freezes.
Oh wait, no, it's Celsius.
Yeah, 0 degrees Celsius, water freezes, okay? And then you can have like negative numbers below that. Oh, -5, -10, whatever it is, right? Well, mathematically, negative numbers in temperature are a train wreck because of the fact that then you're going to have negative values in your equations. Zeros also create train wrecks because then you could either be dividing by 0 or multiplying by 0, so then you have entire sides of the equation which go to 0, which is a train wreck on everything else, okay? So the advantage of the Kelvin scale is that you don't have to worry about zeros and you don't have to worry about negative numbers. So that's the primary advantage of working with the temperature of Kelvin. Now, when you're talking about temperature, this is why you have to study thermodynamics after you study energy. So temperature is the measure of the kinetic energy of an individual particle. Okay? Now, measuring temperature is kind of a cool thing if you think about it. So let's say, I'm guessing in your simpler days, maybe back in middle school, you all had like the old school thermometers, okay, where it had like alcohol in it or whatever, and you'd see where, and you'd put that in the liquid and you'd see what that temperature is, okay? Here's your task for the day. Listen to my lecture on thermodynamics. So let's say, for example, you've got your thermometer. Y'all did this, right? Okay, y'all remember working with the old-fashioned thermometers? Okay? And here's the deal. So let's say you put that into a beaker of ice, right? Okay? So what would happen to the level inside that thermometer?
Go down.
It would go down. Okay? Now here's the deal. If you think about this on an atomic level, here's what happens. You put this in. And thermodynamics is basically nothing more than a measure of the flow of thermal energy. So you take this thermometer, which was at room temperature, and it was showing a certain mark on here, probably, let's say, 20 degrees Celsius, roughly. So what we've done as a species is we've set up an arbitrary scale. We basically took a glass tube, filled it with a red alcohol, and said, we're going to make a mark on here, we're going to call that 0. Okay, cool. And we know that's the temperature water freezes. And then we make these gradations on here, and we know that when that gradations hit a certain point, we say, oh, that's a particular temperature, 20 degrees Celsius, 40 degrees Celsius, whatever. Then we came out here and said, wow, if that water boils, we're going to make another mark up there, and we're going to say that's 100. So basically, we had two known marks. We had 0 and we had 100. And then we divided that up in between equal parts, and that's how we got the Celsius scale. But basically what happens is that on an atomic level, what makes that level rise and fall?
How fast things are moving.
Yeah, how fast they're moving. So you can visualize this, and you can explain basically all of thermodynamics in terms of second grade class full of Timmies. Timmy's bad. Timmy's bad. Okay? But Timmy's bad from a physics perspective, not a chemistry perspective.
Yeah.
So basically, imagine that you have a whole bunch of Timmies in a second grade class, right? And you've got Timmies, and you're going to put them in cold water, right? So at this point, Timmies are going to go, wow, this is really, really cold, right? And if you've ever seen second graders out on a really, really cold day out on the playground, what are they doing? They're huddling up, right? They're not occupying very much space because they're cold, right? Because they're not moving around as much. So you take this thermometer, you put this in cold water. Thermodynamics is the flow of energy. Okay, that's it. So let's say you have a thermometer which is 20 degrees. You put it in ice water. What's going to be the direction of the flow of energy? From the thermometer out to the water, or from the water into the thermometer?
From the water into the thermometer.
From the water to the thermometer. That's the direction the thermal energy is going to flow.
Oh no, the thermal energy is going to go from the thermometer to the water. My bad.
Because here's the deal. Think about
It's
this.
higher now. Yeah.
You take out a bowl of soup, right? It's a nice day for soup. It's kind of cold outside, right? And let's say that that's at 70 degrees Celsius. Okay, so let's look at the big picture here. You take out a bowl of soup at 70 degrees Celsius and you set it out. You come back 10 minutes later. Two things could have happened. Two things could have happened. The air around the soup has gotten colder. And you check the temperature of the soup, and the soup has gone up to 90 degrees Celsius.
That'd be amazing.
Okay? Like, wow, I need to warm up my soup. I'll sit it outside. Okay? And this thermal energy is going to flow from the surroundings into the soup. That's an option. I'm not saying it's going to happen. I'm just saying it's an option. Okay? Now, option B is you take that soup, you set it out at 70 degrees Celsius, you come back, you check it 10 minutes later, and it's dropped down to 50 degrees Celsius, and the air around that soup has gotten warmer. What's going to happen? Second one. Why? What drives anything? Mother Nature is a lazy prima donna. Mother Nature says, screw it, it's too much work to take all that random energy out here and focus it into here to make the temperature of the soup warm up. Like, Mother Nature goes, you want your soup warmed up? Hey, grab a microwave, Jack. I'm not going to do it. What's going to happen is that Mother Nature goes, this is easier. It's easier to go from a high level of kinetic energy in the soup and let that energy flow out to the surroundings than it is to have it flow in. So here's, on an atomic level, here's what happens. It's the same idea. You have a thermometer that's showing 20 degrees Celsius. You drop it into cold water, and that thermal energy is going to flow out from here, and it's going to flow out into the water. So the water actually warms up a little bit, because it's going to take that thermal energy from the thermometer, and it's going to go up. Now, on an atomic level, you have all of these Timmies inside this glass tube. The Timmies are getting colder. What's going to happen to the space occupied by the Timmies? That's going to become less. Oh, it's going to drop to an arbitrary mark that we've determined as human beings and say, oh, it's going to drop to 1 degree Celsius, and that's going to be the temperature. Okay? That's it. So, thermodynamics is nothing but a flow of thermal energy. Now, this is where this gets a little bit weird. So if you look at one of the cool things that we, no pun intended, have going for us as human beings, is that's the ability to sense temperature. Okay? It is. It's kind of a cool, it's a cool survival thing. But if you think about what has to happen to sense temperature, okay? So let me give you two examples. So let me go grab, I don't know, just use my calculator. Okay? So here's the deal. So both of these have been sitting out in this room all day. Okay? So here all you have to do is just take your hand and grab around the 1 kilogram mass, and at the same time just hold the calculator. Okay? All right? Now, do they feel the same temperature?
This one feels cold because it's metal.
Okay? So Kira's saying that the brass feels colder because it's metal. Plastic feels a little bit warmer. Now, here's the deal. I promise you, if you take the temperature, the outside temperature of both of these objects, they're the exact same temperature because they've been sitting in this room all day. Okay? But here's what happens in terms of us as a species. When she grabbed hold of that, she goes, oh, that feels cold. So on an atomic level, this is where this is fascinating. Because Kira has the ability in her hand to sense a flow of thermal energy. So the cool thing about metal, and we'll get into this later, is that metal, it's very easy to change the temperature of metal. It's a great conductor of thermal energy. Plastic, not so much. Okay? So when she grabbed hold of this, her hand was probably about 98 degrees Fahrenheit. Temperature of the metal was probably about 74 degrees Fahrenheit. So when she grabs hold of this, which direction is the thermal energy going to flow? From her hand into the metal, because her hand is warmer. So the plastics is the exact same temperature, but it doesn't feel as cold because of the fact that plastic doesn't conduct thermal energy as well. So when she grabs a hold of this, even though it's the exact same temperature as the plastic, it feels cold to her because her skin has the ability to monitor a flow of thermal energy from her hand into that metal. So she's going to go, it feels cold, because her hand, on an atomic level, is sensing this flow of energy from her hand. It senses that, it sends a message from her hand through her arm up to her brain, and her brain says, wow, I'm sensing a flow of thermal energy that says this is cold. And that's what you sense as temperature. So what you sense as temperature is often just a flow of thermal energy. But that's cool that we have that capacity to measure and realize, wow, this is cold because of the fact that that's what's happening. Now, this is what I don't want you to think about too much, okay? Everybody says, oh, it's a flow of thermal energy. Right, okay. What does that look like? So if you look at your thermometer and you go, okay, hey, this energy is flowing out. And in some ways, a lot of times we think about thermodynamics and thermal energy as a fluid. Because we're saying, okay, this thing is flowing out of here. Well, what's flowing out of it? You say, well, it loses kinetic energy. Okay, so what does that mean? So Kira in her hand is going, that feels cold. So her hand feels cold. It's like, okay, we can articulate that, and we can all visualize what that means, but at an atomic level, what is actually happening? And here's the cool part of this, is that it's actually photons. Because photons carry thermal energy, just like they carry light, just like they carry X-rays, just like they carry microwaves. So basically what Kira was sensing is a flow of thermal energy in what we call the infrared section. Okay, you can't see it, but if you've ever seen like an infrared vision or scope or whatever, where it shows just your thermal images. So basically what was happening is there was a flow of photons, thermal energy photons, in the infrared section from her hand into that brass. Her hand sensed that net flow and says, wow, I'm going to send a signal up to her brain that says, hey, we're losing photons. And then her brain says, wow, I can articulate that idea and go, I'm going to tell Mr. Burkamp that feels cold. Okay? And then, once she forms that thought, then all those neurons fire and send this message to her vocal cords and her mouth, and she goes, wow, I can articulate the fact that this feels cold. And then, on the cooler part, that comes out as a series of vibrations and compression of waves that goes out, hits our eardrums. Our eardrums vibrate with a certain frequency and message that said that sends that signal to our brains that says, wow, we just heard Kira say it's cold. So something that might seem horribly, horribly simple, Kira grabbing a hold of a 1 kilogram mass and saying, oh, it feels cold, is actually a very, very, very complex process if you look at all the intricacies that are involved in that. So it's basically a flow of information as well. Kira is saying, hey, I'm sensing a flow of energy. She's communicating that information to us, and we're going, wow, Kira says this thing feels cold. And we can all relate to that. So something that is very, very simple is actually very, very complex. Okay, so we got this, right? Okay, so temperature flows out, it settles down at about 1 degree Celsius. We pull that out, boom, here we go, we're off to the race. Now, if you take that same thermometer and you put it into a container of boiling water, what's that thermometer going to do?
It's gonna pop at the top like it's a cartoon.
Well, or at least the level is going to go up, right? So why is the level going to go up? Imagine second graders on a hot summer day. Are they going to stay huddled together? No, they're, wow! Okay? It's like you've given them each like a handful of Skittles, okay? Right? And now they have all this energy, they're going, wow, okay, we've got to occupy more space. So they begin to occupy more space. But here's the thing.
Oh my god.
What?
He said Skittle photons, and I was just thinking bear photons.
Oh, the bare photons?
Yeah.
Yeah. That goes back to AP chemistry. Okay. So, I forgot, what was that? What was the deal with the
I don't know, like you said bear.
It was
or something?
absorption.
Huh?
It was absorption.
Oh, it was absorption. Yeah, okay, that was it.
Put more bears in the hallway.
Yes.
Oh, yeah.
Absorbing the photons. Yes, that was it. Okay. Now, here's the deal.
You had to be there.
You had to do it. So, and let's just break this down a little bit farther. So, what is all particles made of?
Stuff.
Stuff. Stuff is composed of.
Stuff.
More stuff. Small.
Just
If you break the stuff
smaller
down,
stuff.
You
get small stuff.
No, you get things.
You get things.
Yeah, you get.
Otherwise known as protons, electrons, and
Neutrons.
neutrons. You break those down, you get into quarks and antiquarks and leptons and all this weird stuff.
Leprechauns?
Okay, leprechauns. And
Leprechauns?
photons and croutons and
Made of resin?
no, those are the fundamental particles of a sound. Croutons.
Wait, did you say leprechauns?
No, it's true. Okay, and then it has the civilization, the fundamental particles of the
Wait,
civilization.
so
are
you didn't
persons.
say leprechauns?
No, leprechauns aren't. No,
Okay.
that's only if you're in Ireland.
Okay.
Okay. So,
That's what Irish people made out of.
so if you look at what happens for us to be having this discussion, we've got protons, electrons, and neutrons, right? And they're all bound together, okay? Which is kind of a cool thing. And so one of the things we've also figured out as a civilization was, wow, how do you manipulate those bonds to make the different things, to make different tables versus, plastic versus brass versus a cup versus milk versus water versus ice, okay? They're all made of the same protons, electrons, and neutrons, but it's how those things interact. So if you look at a liquid, liquids are cool because the fact that they're held together enough that they can still flow past each other, but they're not rigid enough that they're a solid. And so that's the other thing we've kind of figured out how to manipulate. So for example, you get a stick of butter out of the refrigerator, okay? It's pretty solid, right? You let it sit out at room temperature, what happens?
It's soft.
It gets soft. So not quite a liquid, right? But here's the deal though, if you look at that butter though, so something had to change. So what happens to the thermal energy of that butter once you take it from the refrigerator and you put it out in the kitchen? Which direction does the thermal energy flow?
Into the butter.
Into the butter. Oh, right. Now the particles have a little bit more thermal energy. They're not quite locked. They're still not, it isn't like we're going to make the water, it isn't like the butter is going to boil, okay, and evaporate, but it's going to become softer. Oh, now we can spread it on a roll. Right, okay, right. Throw a little jam on top of it. Okay, that's cool, right? So we can take those particles, they're still held together, but they're just not quite held together as rigidly. So liquids are held together, but they can flow past each other. Now, get into gases. Gases are pretty important, right? Because if we didn't have gases, we would not be here having this discussion because of the fact that we kind of have to have this atmosphere. So remember, like on a relative scale, if you take an apple and you cut it in half, and you look at that thin red layer around the outside of it on a relative model of the Earth, that red layer around the apple is our atmosphere. Okay, that's what's keeping us alive, is the skin on that apple. On that same scale, this is all we got, is the skin on the apple. Now, one of the reasons that we still have an atmosphere, we'll talk more about this later, is because we've got a relatively strong magnetic field. And that magnetic field is keeping these gas particles from being blown off when we get these bursts of energy from the sun. And that's one of the reasons why Mars doesn't have an atmosphere, is because it doesn't have a magnetic field. So without this atmosphere that we have, we would not be here having this discussion. So the atmosphere provides us weather. It allows us to breathe. It allows us our blood doesn't boil, because if you put people in a vacuum and things happen, their blood boils and flows. So it's a good thing that we have this atmosphere. So one of the things that, if you look at trying to, we'll colonize Mars. Well, here's the problem if you try and get an atmosphere around Mars, which is composed of these tiny little particles. Number one, Mars has a relatively weak gravitational field. Gravitational attraction on Mars is like 3.6 meters per second squared. We're at about 9.8. So Mars doesn't have a strong gravitational field to keep these little particles from basically going around and bouncing and going, oh, screw it, we're out of here. Okay? And the other thing is that it doesn't have a magnetic field. And so because it doesn't have a magnetic field, even if we could create an atmosphere, you get like the first big solar storm, because it doesn't have a magnetic field, it's basically going to blow that atmosphere away. So that's one of the hardest parts, is going to be, everybody says, oh, we'll just generate all this. We'll take plants up there and we'll grow all, and we'll have an atmosphere. Okay, well, that's fine. But it's kind of like building a house of cards in Kansas, okay? You can do it on a calm day, and you can build a magnificent house of cards. First windstorm comes along, guess what? It's all gone. So that's going to provide an additional challenge of trying to even colonize Mars in terms of building an atmosphere.
What if we made a dome?
Huh?
Like in The Simpsons, what if we made a dome?
Okay, did you seriously invoke the Simpsons in a serious scientific discussion? I just want to make this clear, okay?
I did.
Don't. Because right away, here's the reason I hate the Simpsons, okay?
Oh my God.
No. I did my student teaching at Fort Riley Junior High in the spring of 1990. And that's when the Simpsons first came out. So I spent like about 3 months of my life with junior high kids hearing "eat my shorts," okay? And so I have loathed The Simpsons ever since. Loathed them with a complete and undying passion.
Well, there's like proof other than that. Like, have you seen The Martian?
Huh?
Yeah, exactly. Have you seen The Martian, the movie The Martian with Matt Damon?
No.
way did they
Yeah.
do
You
that.
didn't see it?
You can live in Mars.
Okay.
But then out there, they have like.
I saw them.
He's not just living out there, he's living in
shelter.
shelter.
All right.
Areas.
No, he's living in Mars.
So,
They build a little.
So let's talk pressure, okay? Right now you all are under a certain amount of atmospheric pressure, right? So, and that's about, and if there's ever a physical quantity in science that has an identity crisis, it's pressure. Because it can be in torrs, atmosphere, pascals, kilopascals, psi, millibars of mercury, inches of mercury, centimeters of mercury. Pressure is just all over the place. But here's what you have to fundamentally understand about pressure. So right now, you have about 14.7 pounds of pressure on you per square inch of your body. So Hank weighs roughly about 14.7 pounds. So imagine that you take Hank and you take like a 1 square inch deal, which is about like this, okay? And you take that 1 square inch deal, you put that down, and you put Hank on top of you. That is the equivalent amount of pressure that is pushing down on every square inch of your body. So basically, you have a Hank pushing down on every square inch of your body right now. And don't flip out and go, oh, I feel it. Yeah, I feel that. Yeah, I feel that. Okay? No, you're used to it. Okay? This is what you're absolutely used to. Since you came into this earth, you've been used to it. Now, I'm guessing at some point, some of you might have flown or driven up into the mountains in Colorado. What happens? What?
It's in Colorado, so.
Or flying. Okay.
Yeah, but same thing. You make a lot of jokes about the marijuana. So I thought it was funny.
I know. You do get high. From a pure elevation standpoint. But what happens to your ears? They pop, right? So what happens in this is, and some of you I know have seen this, but physics kind of takes a different slant on this. That's called the ideal gas law, which PV equals nRT. Okay? Perfect. Now, in physics, we have to take a different approach to this than chemistry. And so when I give this lecture, I always have to keep in mind, am I teaching it from a chemistry perspective, or am I teaching it from a physics perspective, because the elements are different. So, let's kind of figure out what everything is here. So the P is going to be what? Pressure. Now, what creates pressure?
Stuff pushing against other stuff.
Yeah, so right now, you've got upon billions upon billions upon billions upon billions of tiny little oxygen and nitrogen molecules, and for the love of God, do not say air molecules. Okay? I will flip out. There's no such thing as air molecules. Okay? There's nitrogen and oxygen. Okay? That's the primary ones. And so, right now, there are billions upon billions upon billions of them hitting you right now. And don't flip out and go, okay? You're used to it. It's okay.
Never did that face in my life.
Now, pressure in a physics classroom is going to be, pressure is force per unit of area. So what that means, and that's fundamentally what it is. What's creating pressure? You have a certain amount of force per unit of area. So pressure in a physics classroom is newtons per square meter. Okay? So these are known as pascals. And right now there's about 101,000 newtons per square meter pushing down on you. So if you consider that a 1 kilogram mass, okay, in round numbers is about, if you multiply 1 kilogram, let's call it 10, it's about 10 newtons, okay? So that means that every square meter, which is kind of about like here, there would be about 10,100 of these stacked on every square meter that there is. Okay, that's kind of the equivalent amount. So imagine 10,100 of these stacked on every square meter. Now, here's the other common misconception that everybody has about pressure. Everybody says, oh, it only pushes down. Well, think about this. If pressure was only pushing down, okay, imagine that I stack 10,100 of those only on the top of that table. What's the table going to do? Yeah, it's going to collapse. So pressure actually is in every dimension. It isn't just pushing down, which is because if it was, we'd all be crushed, okay? So that pressure exists in 3 dimensions. It doesn't just push down. So let's get that misconception out of the way right now. So these are pascals, right? If you divide these by 1,000, you get kilopascals, which is 101, okay? And there's various, sometimes you'll see this as 101,300. Sometimes you just see it as 100,000. Generally, 101,000 is a good working number. Now, volume in the physics class is going to be in cubic meters. So, imagine 1 cubic meter, okay, pretty decent size. So, let's look at the units on this side. So, on this side, when I take pressure, which is newtons per square meter, and multiply that by a volume in cubic meters, I get Newton meters, otherwise known as joules. Okay, that's kind of cool, right? So you're going, whoa, I get joules over here. All right, now. Okay, so let's talk N. Anybody remember? Joe, you better remember what N is.
Moles.
Number of moles, okay? All right, so this is a little bit of a chemistry throwback, okay? So if you have like 1 mole of, Nick, if you get this wrong, so I'm going to go back and change your AP chemistry grade. If you have 1 mole of carbon, how many grams of carbon do you have? You can look at the periodic table.
I can't see. I don't remember how to read it.
Nick can't read. Look at me.
Shut up.
Look at me.
Well, you're looking at lithium.
Look at me.
I know, I'm reading the
I'll save it.
I'm like an old person.
Welcome to my world.
I'll save
You
it.
still got your gallbladder, be thankful.
It doesn't say the weight. I mean, the mass. I don't.
Let me give you a hint, it's 12.
It's there, right there. It says 12.
Yeah. Okay, you're welcome. Because that's a relative atomic mass measured in grams. Okay? Now, for the bonus question, for those of you that are taking Chem 1, how many carbon atoms does it take to sum up to 12 grams?
6.02.
6.02 times
20.
third.
Third, okay.
Avogadro's number, right?
26.
Avocado
Yeah,
number.
now, in physics, we work with kilograms.
That's why we can't afford
So
houses.
relative atomic mass is actually kilograms. So it'd be like 12 kilograms, so that would take 6.82 times 10